the oil is super soggy on the inside.
It just tastes like
Deep fried part of it very
Yeah, if you do it right, there should be nothing soggy in a deep fried something. Except in deep fried pickles. Deep fried pickles, it's okay for those to be soggy on the inside because that's the nature of a pickle. But a deep fried Oreo should not be soggy on the inside. Yeah, that might be what happened there.
We'll never be eating fried Oreos.
Right. All right, good morning, everyone. Welcome back to Physical Geology 1403. Yes, I am wearing a jacket. I am actually cold today. Come on, camera. I know, right? It didn't think it was possible? No, 23 degrees. We finally found Professor Hart's limit. For a sweater, anyway. All righty. Oh, I need a widescreen map. So, I have graded all exams that were turned in as of yesterday. If you have not looked, feel free to do so. If you do not like your exam grade, well, there's something we can do about that. It's a process I call tutoring and asking questions. Okay? Make the exam review better for you. And yeah, the only way to make that happen is by taking better notes, asking questions, and getting tutoring when you need it. All right? Very few people have taken me up on the tutoring option. I am available during most points in the day if you schedule it with me in advance. My LRC tutor, Sue, is available most evenings if you schedule with her in advance. So please, if you feel like you need the help, take the time to get it. We're available. What are you drinking today, Abigail? An iced lemon what? Ice? Wow, okay. Cinnamon roll. That sounds good. Is that like a coffee thing? All right, I'll never know. I don't drink coffee. I don't actually drink those either. Red Bulls. I think that would kill me. I have a caffeine hypersensitivity. One drink of Coke and my heart starts racing out of control and I see spots. Yeah, I think a Red Bull legitimately would probably kill me. 5-hour energies puts me in the ground, I would bet. Anything. I have to avoid it. All right. So let's see. That's your first exam. That's out of the way. That's all done, hopefully. If you have not taken it yet, please take it. Okay? I will still grade it. Past this week, you're going to start getting some major point deductions if you don't take it. So hopefully, if you haven't and you're watching this, you decide to set some time aside. What else? Oh, there were a few things on the exam I noticed. If you don't know the answer to a question, first of all, that's a weakness in your notes, right? But also putting NA. I don't know if we all know what NA means. NA means not applicable. Answers to test questions are most certainly applicable, right? So if you don't know, you can say I don't know. I interpreted when people put NA as I don't know. I just wanted to point that out. Answers on tests are most certainly applicable. Just want to make sure that's understood. Okay. Any questions at all about anything whatsoever? No? Nothing? We good? No fun facts? Yeah.
I made fan art of your snake.
You made fan art of my snake. Can I see it? Wow, that's a first. He has fans. I knew he had fans. I just didn't know any of them would go so far. Let's see this. Hey, yo! Look at that! I love it.
Look at the computer right there.
Metamorphosed, igneous, Can I get a picture of that? Thank you. I wasn't going to finish reading the rest of that because this will go on YouTube. And I don't know how anyone would interpret that or clip that. Okay. Excellent. Thank you for sharing. I love that. Anything else? Anything in the news? Nothing? Okay. Well, today is lecture 9, the second lecture in module 2, which, as you can tell by now, is all about external Earth processes. How the things that we learned about what the Earth is made out of and the way that processes on Earth work, we're exploring each part of that in its own unique sphere, right? So today we're talking about glaciers and glaciation. Very appropriate day to talk about glaciers, wouldn't you say? 23 degrees outside. How many of you have ever been to a glacier? Have you ever seen one? I'm assuming you've never licked one then. I've licked a lot of glaciers. In case you can't tell, the number of weird geological phenomena I've licked is a matter of pride. It's a way of making my mark, I guess. Okay. Before we start talking about glaciers, though, we need to talk about something else before that. Something incredible, something you all take for granted, something we talked about last time, actually. Let's talk about water, right? Who doesn't love water? I dated a girl one time decades ago who never voluntarily drank water. Alyssa is nodding her head emphatically. You also do not voluntarily drink water? You have a Gatorade. Okay, well, that's better than this girl. This girl would only drink Dr. Pepper. She would drink nothing else. Trent is pulling his drink closer to himself. I don't get the appeal personally, but that's obesity waiting to happen. I'm just going to put that out there. If you only drink water, or if you only drink Dr. Pepper, just be ready for that. That's diabetes at 30, right? But I don't understand. My personal favorite beverage is, in fact, water. This is a cup of water here. This is my favorite. And, oh, it's so good. Right? You need water. Water is everywhere. Water is part of us. Water is part of all life as we know it, as it has formed here on Earth, if on Earth it formed in the first place at all. It is required for the forms of life that we have. So let's talk about some of the ways that water is so incredible. What makes it such a unique substance? First of all, water is probably the most common 3-molecule chain in the universe, as far as we can tell. You look out into space and you see water reflecting back at us through all our telescopes. The wavelengths that reflect off of things, certain greenhouse gases, for example, large molecules, like what we have in our atmosphere, will reflect light and radiation better than other ones. And so that's how we can tell what the atmosphere of other planets are made out of, for example, just by looking at them through a telescope. We can see so much water in space. It is extremely common, okay, which is pretty cool. Explains why we probably have a lot here. Water has something called cohesion. When you're driving down the highway, and it starts to rain, blip, 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 on your windshield, what do you notice about the raindrops on your windshield and on the hood in front of you? You get a raindrop and it lands. Does the water spread out? No, it stays in a bubble sort of shape, right? This is cohesion. Water likes to stick to other water molecules. They bind together very well, okay? Oil doesn't do that. You put oil in a pan and it'll just spread out. The thinner the oil, right, the less viscous the oil, the more it'll spread. Vegetable oil versus olive oil, for example, right? And then you have things like coconut oil that are solid at room temperatures. So there are different levels to this. But say a vegetable or a peanut oil, you put that on a flat surface and it'll spread out as thin as it possibly can. But water, no, water prefers to stay, if possible, grouped together in that sort of bubble, right? This is cohesion. This is why we have bodies of water, why water isn't just spread out everywhere. Water flows into rivers. Water collects in lakes, okay? It has cohesion. And then there's its energy absorbing properties as well. Water will absorb energy slowly, but retains it very well. you put your pot of water on the oven, it'll take a while to heat up, right? But it'll take even longer to cool off. There's actually a very practical historical example to this, okay? Long, long ago, not in a galaxy far, far away, in this one, on this planet actually, when communities were based on fishing industry, okay? We have a village, say on the coast of England, and their entire economy, sustaining themselves, is based on the fish that they catch every day. Okay, we're talking thousands of years ago, okay? So they take their boats out to go fishing and then bring them back in the evening. They use sails. In the morning, when the sun rises, it starts to heat up the land and the ocean. The land heats up quickly. The ocean heats up slowly. Because the land heats up quickly, it starts to radiate heat off of itself, releasing some of that heat into the atmosphere above it. Warm air above land and cold air above ocean. I don't know how much you know about meteorology, the study of weather, but warm air makes a high pressure zone and cold air makes a low pressure zone. And high pressure moves into low pressure. And so this makes a breeze that goes from land out to sea. And guess what? That morning breeze carries the sailboats out with it. They figured this out. There's always a breeze that goes out to sea in the morning. Let's ride that out to sea to do our fishing. At the end of the day, the sun is setting. The land absorbed that heat quickly, making that hot air above it, but it also loses it quickly too. And so the land starts to cool off quickly while the water, which has been warming up all day, loses heat slowly. It holds it more efficiently. So now we have warm air above the ocean and cold air above the land. And what direction does that make a breeze? From the ocean back to land. And guess what? Those sailboats ride that breeze back home with their catch for the day. This is actually where the concept of the workday came from. You go to work in the morning with the sun and you come back at the sunset. This fishing industry was part of what established that in our cultures. Okay. Now we've adjusted that to more of a 9-to-5 sort of schedule for most people, right? But that's just because of modern perception of, I don't know, fair work practices or some nonsense, right? Who really works 9-to-5? I mean, there are some people that probably do. Newsflash, teachers work more than that. Okay, so this is another property. It holds heat efficiently, okay? And then there's another thing. What happens when water freezes? What happens to most things when they freeze? What does water do? Say it louder. It expands. What do most things do when they freeze? They contract. Yeah, most things, when they go from a liquid to a solid state, will actually contract. They take up less space. Their bonds are tighter together in that molecular bond, in that crystalline bond, right? But ice expands by about 9%. What does this do? We're increasing what? Volume. What stays the same, though? Mass. So if my mass stays constant and my volume changes either up or down, what is changing? Huh? Density. Good. Density is a measurement of mass per unit volume, right? So if my mass stays constant, but my density increase or my volume increases, my density goes down. Good. And this, my friends, is why ice floats on water. The exact same chemical signature here. H2O is still true in both of these substances. The difference being ice has expanded a little bit, decreasing its density, therefore allowing it to float on water. And that's why you have cubes of ice in your drink. Okay? Or those fun chewable pegs of ice if you go to Sonic. Right? This principle is the same. Ice is ice is ice. This is why glaciers float on water. Now, not much of the ice stays above the water. Think about a glacier, for example, or not a glacier, an iceberg, okay? Think about an iceberg. Think about that poor Titanic, right? Hashtag Jack could have fit on the door. If you know, you know. If you don't, watch Titanic. Why is it difficult to see an iceberg? Because there's not much of it above the water. Just a little bit of it. Only about 1/7 of an iceberg is actually above the water. The rest is under the surface. Why? Because even though it is less dense than water, it's close enough in density that it doesn't all stay on top. Think styrofoam. The difference between an iceberg and styrofoam. Styrofoam, hardly any of it goes below the surface because the density is that much different. With an iceberg, it's only 9% off, right? So most of that iceberg is still going to be underwater. Okay, so what does this have to do with glaciers? Someone remind me what the definition of a mineral is again.
An inorganic solid with a crystalline structure and a chemical formula.
Inorganic, solid, crystalline structure, chemical formula. There was one more characteristic. You got 4 of the 5. Naturally occurring. Any naturally occurring inorganic solid that possesses an orderly crystalline structure and can be represented by a chemical formula. Did we already figure out that ice qualifies? Yeah, we did in like day 1 of the class, right? We made that observation. Ice is, in fact, a mineral according to the geological definition. And so the study of bodies of ice falls under the category of geological sciences. What is a body of ice? Well, glaciers. So we have our ice, which is made out of all this stuff, qualifies as a mineral, and believe it or not, this mineral can move. Masses of this mineral making glaciers. These glaciers move. Y'all are familiar with the concept that glaciers move, right? That's not a newsflash to anyone. If it is, your life is forever different, right? But glaciers do in fact move. How do they move? We describe their movement as plastic movement, plastic behavior. What does that mean? What does plastic mean? Someone tell me what the word plastic means. While I drink some water.
Like dynamic, it changes because plastic can be molded.
Ah, okay. We've cut right to the chase. When I say plastic, what's the first thing you think of? Go. Plastic. What's the first thing that comes to your head? Is it fun? Mean Girls? I'm so curious about why. I haven't seen it. Okay. I guess I need to see Mean Girls. Water bottles. Good. What do you think of? Nothing? Plastic doesn't exist. Ray,
I
plastic.
think of plastic cups.
Plastic cups? Okay, we'll get there in a second. Abby? Blow dryer? Milk jugs. Oh, okay. Yeah. Anyone over here? Sage? Plastic. What do you think of? Dinosaurs? Look around at all the stuff around you, right? She looked around at the table for inspiration of something made out of plastic. Look at everything in this room, at all the stuff made out of plastic. Are they all the same substance? No. There's this plastic and that plastic and this plastic. That dinosaur is not made out of the same plastic that this cup is. That cup is not made out of the same plastic that this remote is. This remote is not made out of the same plastic that your laptop cases are. So many things in our world are made out of this stuff that we just call plastic. All the things that we call plastic are actually dozens of different types of chemical polymers, right? That we, as Marquez said, mold and shape into the structures, the tools, the objects that we need. That's what the word plastic means. I want you to think of the word plastic now, not as being a substance, but as being an adjective, a descriptor. This is plastic, not because that's the name of the material. This could be PVC, it could be PLA, it could be ABS, it could be any number of things. But we call it plastic because it was moldable, shapeable, changeable into what I needed. I was able to use forces like pressure and heat to make that object plastically. So when I say that glaciers move because they are plastic, it doesn't mean they're made out of this, right? It means that they are moving plastically. They have plastic behavior. They are changing their shape based upon forces. What forces do you think are causing glaciers to move?
Gravity.
Gravity. Huge. Yes. All right. Well, good. Let's keep moving, and we'll keep talking about that. A glacier itself is a very thick mass of compressed ice. It can be anywhere from hundreds to thousands of feet thick and take thousands of years to make. There are some glaciers that have been around for millions of years. There are some glaciers that have been around for less than 1,000. There are glaciers forming right now. There are many glaciers melting right now, right? Glaciers act as forces or agents of both weathering and erosion. A glacier that is only a couple hundred feet thick can weigh millions of tons of ice. Ice is softer than pretty much every mineral it could come across. But if I dumped 1,000,000 tons of feathers on you, Daisy, what do you think would happen to you? Yeah, you'd go flat. Maybe molecular thin flat, right? It's like that old math trick that all our kindergarten teachers played on us. What's heavier, a pound of rocks or a pound of feathers? A pound is a pound is a pound is a pound, right? So no matter how soft the material is, if you get enough of it, it will crush anything. So we've got millions of tons of ice flowing over rock, crushing, pulverizing that rock as it goes. That's weathering, mechanical weathering. And then it transports that material downhill, right? Erosion. Glaciers represent the vast majority of the fresh water on our planet. Remember, only 2.15% of all water on Earth, or excuse me, 2.8 of all water on Earth is fresh. And of that 2.8, 2.15 is in glaciers. Most of it is in glaciers. It's a lot of fresh water. If you were to melt all the glaciers in Antarctica and add that to the oceans, our oceans would rise by about 60 to 70 meters. A lot of meters. It's even more feet, right? This is what North America, this is what the United States of America, it's not showing all of North America, would look like if that were to happen. Florida, gone. The entire East Coast, gone. New York underwater, gone. Houston, gone. Memphis, Tennessee, gone. Because the entire Mississippi embayment has been flooded up, right? San Francisco Bay, huge. San Francisco, gone. Seattle, gone. It's right there on the Puget Sound. All these cities around Hudson Bay, gone. Remember what I told you? 70% of populations live on or near coastlines and will be affected by rising sea levels, right? That's a lot of people. That's if all the ice on Antarctica melted. This is a fun tangent. What about Antarctica? If I were to just take a giant hairdryer and melt all the ice off Antarctica, what do we then have there, by the way? What's under and what is Antarctica?
The desert.
A desert?
Ocean.
No,
Just a sheet of ice.
it's not. This is the big misconception. So many people think that Antarctica is just a massive sheet of ice. There is a continent under there, a massive continent, way bigger than Australia, underneath of all that ice. It's been covered in ice for about 50 million years. An entire continent that has not been explored, that we can't see unless all that ice is gone. Unexplored. Think about, and I guarantee this is what every other nation thinks about too, right? It's an entire continent with oil reserves that have not been used, with precious metals that have not been found. And where my head goes, an entire continent of dinosaur fossils that haven't been discovered, right? So much stuff under that ice. There is a thing that exists called the International Antarctic Treaty that prevents any one nation from setting up any exploitative venture on the continent of Antarctica. First person that breaks that treaty, everyone else gets mad at. So far, it's held. But as resources get thinner, as we face more choices like, well, is it moral to chop down our rainforests to look for bauxite to mine? Or should we go to this completely uninhabited continent and do it there? Obviously, not that many forests, but mine there, right? Which one is moral or more moral? These sort of questions are going to become more and more common as our need for resources gets more and more desperate in the developed world. So I anticipate the conversation around Antarctica will probably heat up here probably in a little bit. Not that long. A couple of decades, I'd say, before people start genuinely thinking, is it worthwhile to break the treaty so that we can satisfy our nation's resource needs? We'll see. Anyways, that's Antarctica. Whole undiscovered continent. Well, we know where it is, but, unexplored, so to speak. Okay, so there are different types of glaciers. The first type, the more common type that you're going to see most often in pictures and whatnot, if you think glacier, people typically think valley glacier. This is simply a glacier making its way downhill through a glacial valley. Okay. Usually these end up at the bottom of the hill, wherever the valley flattens out, at the bottom of the mountain, whatever it's flowing down. And a lot of the time they actually empty out into bodies of water as well, like this one. This is Hubbard Glacier, and it empties out into Disenchantment Bay. This is in Alaska. Okay. By the way, this is an infrared map. IR. Any of y'all know what this red is? Huh? It's not heat. Not rock. On infrared maps, red, in fact, represents life, vegetation. Yeah. So what you're looking at there is an IR, infrared overlay of all the plant life around a satellite picture of the same area. It's pretty cool. Okay, so what are we looking at here? We're actually looking at two glaciers, the Valerie Glacier and the Hubbard Glacier, that combine together and make the larger Hubbard Glacier, okay, where it empties out into Disenchantment Bay here. This is a valley glacier. Then you have ice sheets. Ice sheets are the largest masses of ice on Earth. There are only two right now. One in Antarctica and one in Greenland. Which one do you think is larger? No, actually say it. Do you think Greenland is larger or do you think Antarctica is larger? Thank you. Good. Yes. Okay. Antarctica is the location of the largest ice sheet. Okay. In an ice sheet, ice is sourced from a central location. It's formed here and then kind of flows out from there. Whereas with a glacier, it's formed at the top of the glacier and then flows downhill to the bottom, right? This kind of forms out here in this snowfall area and then gets pushed out in all the different directions. Because it shares the same source area, we refer to all of this as being part of an ice sheet. Now, there are individual glaciers part of that ice sheet, but they are all a source from the same area. The same thing is true from Greenland, up here near the North Pole. Sourced from up here near the Arctic Circle, up here in the Arctic Circle, and it spreads out from there. Yeah? Why is it called Greenland? Because good old Leif Erikson, Norwegian explorer, landed there, and he landed in a place that was densely forested, and thus thought that the entire place was. And so they started calling it their equivalent in their language of what translates to Greenland, because he thought it would be a land of plenty, a land full of life, where they could go and explore and just be vast forests and places that they could set up communities and all that. And they called Iceland Iceland because they landed near a glacier on Iceland. Even though Iceland has far more vegetation per square area than Greenland does, the names really should be switched, because Greenland is almost entirely covered in ice and Iceland actually has a lot of trees. But the name stuck because that's where the original Norwegian explorers found. They also, incidentally, those explorers found North America long before Christopher Columbus did. For those of you that don't know, there are actually wrecks of ancient Norwegian Viking exploratory ships that we have found in the mud along the east coast of the United States. And I believe, I don't know if this has been fully corroborated, so don't quote me on this. I believe that there are actually Native American accounts of people with the description of Vikings from the tribes along the East Coast interacting with the Native American populations. I believe the Vikings have a name for them. Skraelings, I believe, is their name. They referred to Native Americans as Skraelings and came back with tales of them. And they entered the lore of ancient Viking mythology. Very fascinating things coming out through a study of archaeology these days. Okay. Then there are ice caps. Ice caps you can think of kind of much smaller scale ice sheet, where again you have that sort of central source area and it spreads out into the glaciers from there. But this tends to take place in more localized mountain ranges and less over, continental wide areas. So ice caps, same concept, just over mountain ranges instead of entire regions. And then you have outlet glaciers. Outlet glaciers look like this, where you can kind of think of it as a glacier that's kind of gone rogue from an ice sheet or an ice cap. Okay, it's kind of gone off on its own path, left the rest of the pack, so to say. Okay, and just kind of dies out somewhere else because it's gone so far from the source area. And then a Piedmont glacier looks like this. Now I'm curious, does this shape remind anyone of anything? The Land Before Time? Yeah. I really want to know why.
Oh, does it remind you, like, when they find that whole entire, vegetated area towards the end of the movie?
Oh, are you talking about, what do they call that? It's the place they were trying to find the whole time, right? Yeah. I want to say Hidden Valley, but that's Ranch. I don't remember what it's called. It might actually be the Hidden Valley? Okay. All right. Yeah. It's been a while since I've watched The Land Before Time. I should get my kids into that. They're too young for Jurassic Park, which means their Land Before Time would probably hit hard. All right. But what else? What else does it look like? Anything that we've talked about before? Anything perhaps we talked about in our last lecture? What? River deposits. And what do we call that? When a river flows out and drops solid sediment, what do we call that structure? Huh? Say it so much louder.
Delta.
Perfect. It looks like a delta. This looks like a river delta where the river enters an area of flat or like a flatter area or a like a larger body of water, loses all that energy, drops all that sediment and spreads it out. And you get that fan shape. We call that on land an alluvial fan, and in the water a delta, right? Doesn't that look like this? What's happening here? Our ice is flowing out of the valley, reaching the bottom here, losing its gravitational energy, spreading out, and dropping its sediment. This solid water is behaving the same way the liquid water does. How crazy is water? It's nuts. It's cool. Nothing else does that. All right, y'all think I'm crazy. All right. Well, in that case, let's talk about how we make a glacier. Okay, we're going to make a glacier together as a class. What do we need? Tell me what we need to make a glacier. What are the ingredients? Water? Yes, and that water needs to be cold. It needs to be ice, okay? So we need to have water falling from the sky as ice. What do we call that? Snow. That's it. That's what we need. We need snow. Where do we get snow? Ah, yes. Why do we get snow at high altitudes? Why is it colder up high?
Pressure?
Pressure, not so much. Hmm? Okay, the atmosphere gets thinner.
Which means there's less atmosphere to hold like the heat energy.
Okay, so there's less stuff to hold heat energy. And the higher up you go, the more dispersed it gets, right? Yeah, all of this. So we have high altitudes, which equals low pressures. Sorry, not pressures, temperatures, okay? What that means is that anywhere along the surface of our planet, you can look up, and at some point you won't be able to physically see it. Don't actually look up, right? But there will be, at some point above your head, a line above which it is cold enough year-round for snow to remain. Now, that doesn't really make a difference to anyone or anything if it's high up in the sky, right? If it's just up there, okay? So airplanes fly up there. That's why you get little ice crystals on your window when you fly. But that doesn't make a difference. That will make a glacier unless what? This is the other ingredient we need. So it's all well and good for temperatures to be cold up high, but a glacier won't form unless there is what up there? Not wind. Am I just going to get giant blocks of ice forming in the sky? No, they form on something.
You need a mountain.
You need land up there. You need some body of land, rock, to have gotten pushed up, usually through tectonics, exclusively through tectonics, right? Up that high, so it goes past that snow line way up in the sky, and then snow can fall on that land and be cold enough year-round to remain. That line is called the snow line. Okay, and where mountains go up past the snow line, we have glaciers forming. Think about, this is Mount Kilimanjaro. Anyone want to guess where Mount Kilimanjaro is located?
Africa.
How do you know it's in Africa?
There's a giraffe.
There's a giraffe there. That's a pretty good indicator, right? Yes, this is in Africa. This is actually in a country of Africa called Tanzania. Okay. Have you ever seen the gemstones Tanzanite? If you ever go on a Carnival cruise, they will try and sell you so much Tanzanite. Beautiful, deep blue gemstones that are only found here at this volcano. This volcano has a very unique chemical signature to its rock, so that while this volcano was forming, tanzanite crystals formed. It's the only place in the world you can really find them. So they sit somehow Carnival cornered the market on tanzanite, and that's what all their jewelry has on it. But yes, what do you notice here on the slopes of Mount Kilimanjaro? Snow, ice, it's white. There's stuff up there. Starting at a certain elevation. What do you think I can call that elevation?
The snow.
The snow line is right there. How do I know? Because there's snow above it. The snow line is the point, the line at up high in elevation, above which snow can exist year-round. You don't really think snow or ice or glaciers when I say the words Tanzania, Africa, and yet there it is. The same thing is true for Hawaii, by the way. I have had snowball fights with my brothers on the slopes of a volcano in Hawaii. Why? Because that volcano is above the snow line. Regardless of what else you think about Hawaii, hot, humid, vacation, beaches, there is still snow above a certain elevation. That's your snow line. So now we have snow falling above our snow line. It compacts, okay? You get those nice hexagonal crystals of snow that fall and they collect. By the way, how many of you learned in school that every snowflake is unique and none of them are ever the same? Any of you learned that in school? I am so sorry. That is a fat lie. I know. I just broke your heart, didn't I? No. There are actually only about 26 possible crystal configurations that they can make, which is probably, that's a large number. It's probably where this rumor started, this myth about snow crystals, right? You collect enough of them, so many of them look different that it's hard to find any that look the same. But a close examination over many years of gathered data has shown that there are actually only about 26 crystal shapes they can have. They're all different variations of hexagonal shapes, but there are. Regardless, so whatever shape they fall as, they collect in these snow drifts up there, and then the wind comes and it blows them this way and it blows them that way, and our nice hexagonal delicate crystals have little bits and pieces chipped off of them until finally we end up with tiny little rounded stubby crystals of ice. We call that firn, F-I-R-N. And it is that firn that compacts as time goes on, layer upon layer upon layer, and forms that dense, hard glacial ice. Does that process sound familiar to anyone? Tiny little pieces of crystals that get moved this way and that way, and pieces get broken off of them until getting compacted into a denser substance. So we have weathering. This is the sedimentary process. Connection made. We take crystals of ice and put it through essentially the exact same sedimentary process that, say, sand goes through to become sandstone. That ice goes through and becomes a glacier. Right? Same thing. Okay. So that's how we make a glacier. Any questions about making a glacier? Don't try this at home. It won't work. Unless you happen to live above the snow line. Actually, there is a place in India, I want to say, where they are artificially making glaciers. They actually pump water up a mountain, spray it out onto the side of the mountain, and it becomes snow as it falls down through the atmosphere, right? It's spraying really high, so it goes a couple hundred feet up, freezes, falls as snow, and then over time compacts, and they are artificially making a glacier up there. It's very interesting. Yeah?
Why?
Yeah, that's a great question. Why? Long-term goal. They want to, it's kind of an experiment, but also the glaciers in that part of India have significance to the ecosystem, but also the culture, if I remember correctly. And so they've put all this monumental effort into trying to make a glacier remain up there so that nothing changes. Because that glaciers are up there are melting. And so they're trying to keep it there as long as possible.
Sounds a little expensive.
It is expensive. Yes. There are many expensive things that people and governments do that don't make a lot of sense, at least to us. It may make a lot more sense to them, right? We got to reserve some judgment, right? It may sound like a waste of money to us. It may not sound like it to them. Any other questions? All right, well, let's talk a little bit more about the ways that glaciers move. Did I push the button? I did not. Okay, let's talk a little bit more about this plastic flow. How does it happen? Why does it happen? Plastic flow, again, is the deformation of this material, this ice in this case, under pressure. Think of Play-Doh, right? If I have a ball of Play-Doh in my hand, is it just going to change shape randomly? No. What is required for that Play-Doh to change shape?
Pressure.
I need to exert pressure on it. And then I can mold it into any shape I want by applying pressure in the direction I need to make that shape. Plastic flow is very similar. What direction does gravity push things or force things or pull things? Down, to our perspective, right? It's going to pull things down. That's what gives things weight. Do you know the difference between mass and weight?
Yes.
Mass is the amount of stuff in an object, and weight is the result of an equation between that mass and the force of gravity on the celestial object that you are near. Okay? Which is why when you go to the moon, you weigh less even though you have the same mass that you do here. When you go to Mars, you weigh slightly less than you do here. Okay? So as you gather more mass, the weight increases because the mass is changing while the force of gravity remains constant. Therefore, you hit a certain point of pressure, an amount of pressure generated by that weight when all of a sudden our solid ice that is rigid and unmovable becomes plastic. Once you reach that pressure threshold, the ice on the bottom of our glacier will deform. It will mold like that Play-Doh does as it moves downhill. Our glacier is moving downhill by deforming plastically. Now, how much pressure is necessary? I won't give you the kilobars, but it takes about 50 meters of ice. The weight generated by at least 50 meters of ice is required for plastic flow to occur. About 170 feet. Okay? It's a lot of ice. Anything below that point can deform plastically. So if I have a glacier a mile thick, which sounds inconceivable, and yet during the last ice age, there was a mile thick glacier in the middle of North America. Okay? If I have a mile thick glacier, that's a lot of weight. There's a lot of plastic deformation on the bottom of my glacier. Right? Now, there is another form of movement called basal slip. However cold your glacier is, the rock that it is sitting on top of is often a little bit warmer than that ice. Geothermal activity, whatever the case may be, it's usually a little bit warmer, which means that there's a very thin layer of water between that ice and that rock. And so every now and then, the glacier will slip forward on that thin little layer of water on top of the rock. And that's called basal slip. It doesn't make up for as much movement as the plastic flow, but enough to be worth mentioning. Okay. Now, let's talk a little bit about the rate of movement that a glacier experiences. Way back when, in Europe, shepherds high up in the mountains would come down and say, hey, you know those big walls of ice up there? Yeah, those things move. And people be like, no, those things don't move. We've never seen it move. They can't move. That's too big. How would that move? You're crazy. And yet the shepherds would say, no, my grandfather saw rocks on it here, and now I am here, and I see that they're further down the valley. And So it went back and forth for a while until finally someone decided to experiment and figure it out. So in 1874, a study team, I forget exactly which country this was in, but they planted flags across the entire surface of a glacier in a straight line, valley to valley, valley side to valley side. And then they came back in 4 years, 1878, and you know what they found? They found that their straight line of flags was no longer a straight line, it was a horseshoe. And then they came back after that, 4 years after that, and found it was an even more exaggerated horseshoe. What does this tell us about the movements of glaciers? Do they move?
Yeah.
Yes. But how do they move?
The center moves faster.
The center moves faster. The center stakes moved faster, further than the sides did. Does that remind you of anything? Ah, like a river. Didn't we learn last time that rivers have more energy and therefore move faster? Where? In the middle. So do glaciers. Same behavior, but as a solid. Water is nuts. Water is crazy. Water is cool. Right? There's another bumper sticker I should make. Water is crazy. All right. Y'all know what a budget is? I promise I'm not changing the subject. What is a budget? Here, who hasn't spoken yet? What's a budget?
Something you keep track of?
Something to keep track of? Sure, let's elaborate on that. Jose, what's a budget?
Like how not the maximum, but like
See, I'm getting the impression you all don't have budgets. Oh, to be a teenager again. Right?
It's like an amount you have like available to spend.
Right. It's an amount that you have available to spend. Let's elaborate on that. Normally, when you have a budget, it is to prevent you from spending more than you bring in. If you, newsflash, if you spend more than you've got, you get in debt. Debt's bad. You don't want to be in debt, okay? Credit cards, that's a whole other thing. Think of credit cards as controlled debt. Don't think of that. I just all of a sudden became an economics class. Don't think of credit cards as something that you can or should live off of. That should be for emergencies or very carefully balanced debt, right? Having a constantly maxed out credit card is not going to do you any good. It will be, in fact, detrimental to your well-being, okay? Because they'll come after you for it. However, if you have, say, let's say I bring in $1,000 dues a month, okay? And then I spend $800 dues by the end of that month, I have an excess of $200 dues that stay in my bank account, right? That is a positive budget. A negative budget would be bringing in $1,000 dues and spending $1,200 dues. Not a good idea, okay? The same thing is true for glaciers, believe it or not, except glacial budgets don't have to do with money. What do you suppose glacial budgets have? What do they need to balance?
ice,
Ice? Well, what comes before ice?
snow.
Snow. We need snowfall before we can have ice, right? Yes. So snow input versus snow removal. That is the budget. Okay? So what does this mean? I have on all of my glaciers a zone that I call the zone of accumulation. This happens above our snow line. Why? Because the snow line is defined as the line in space above which snow remains year-round, right? It won't go away up there. So here I have my snow line, and above that is my zone of accumulation. Snow falls, ice forms, flows downhill. Beneath the snow line is the zone of wastage. What do you suppose happens there? Huh? It is. It's wasted. What do I mean by wastage? What could happen in the zone of wastage?
The snow melts.
Melts. Well, it's not snow at this point, right? It's ice. Yes. Okay. So we have melting. We have icebergs breaking off. We call that calving, by the way. When a chunk breaks off of a glacier, we call that calving. When I was in Alaska in May last year, I was on the boat and we were just kind of hanging out in a bay. It was a beautiful sunny day, not a cloud in the sky, and all of a sudden here, like, what is that sound? There's no thunder, there's nothing, there's no rocks falling or anything. And I looked down the valley where I could just see the glacier at the end of the valley, and there are humongous chunks of ice just falling off it. But it sounded like rolling thunder all the way from where I was, probably a mile or two away from it. It was impressive. Call that calving, okay? When any chunk falls off the front end there, okay? Let's go back to our topic of a budget, though. If my snow is receiving more, if my glacier is receiving more snow than it's losing, would you call that a positive or a negative budget? It's gaining more than it's losing.
Positive.
Positive. We all want to be there, right? We all want to make more money than we spend. That's great. Glaciers need that too. If a glacier has a positive budget, a positive mass balance, you can think of this, okay? Then my glacier will continue to move downhill. It'll keep moving forward. What if the opposite is true? What if I am losing more? What if I'm melting more ice at the bottom than I am gaining snow at the top? What happens?
It's a negative.
It's a negative one, but what happens?
The glacier melts.
The glacier melts. Where does the front of my glacier go? Yes, it retreats. And this is where I get two terms that you'll need to know: advancing glaciers and retreating glaciers. An advancing glacier is one that is receiving more snow input than it is losing ice at the bottom. And so the front of my glacier will continue to advance forward. A retreating glacier is the opposite. It is not receiving enough snow above to offset the melting beneath the snow line. More melting here than deposition there, right? So what's the front of my glacier going to do? Melt backwards. Now, this is very important. Pay attention to this terminology here. At no point is the glacier pulling upwards. Why? Why do I want to avoid that wordage? If I'm pulling something, I'm using energy to bring that thing this way, right? Glaciers are not doing that. They cannot pull. They can't make that choice in the first place. But also, that's against gravity. You can't go against gravity if you're a natural, right, phenomenon like a glacier. You have to go where gravity's telling you. So a retreating glacier still has snow going downhill, forming ice, making more to that glacier. It is simply that loss is greater than gain. And so the front of my glacier is melting uphill. The front is continually retreating uphill because it's melting faster than it can be renewed. That's all. No pulling at all. All right? There was one more thing I wanted to say, but I don't remember what it is. It'll probably come back to me. It'll probably come back to me around midnight tonight. That's probably when I'll remember. Okay. Let's talk about the effect that glaciers have. I've already mentioned that they work as agents of weathering and erosion, pulverizing that rock as they move downhill. That's how you go from a small valley to a large valley, as it has more and more glacial ice moving through it as time goes on, right? Even though it moves plastically, it is still a solid. And so anything it picks up, it's going to hold on to until the point that it melts. And so what glaciers end up being are essentially massive conveyor belts for sediment. So they'll pick up stuff, carry it miles and miles and miles downhill, melt, and then drop that stuff there. When we have large amounts or large objects, they get picked up and transported. We call that plucking. Okay, something got plucked up from here, transported, and deposited over there. It then becomes what we call a glacial erratic. An erratic. It shouldn't be there. That object is foreign to that location. This rock, for example, what is that doing there? How'd that giant chunk of rock get here in the middle of this plain? It shouldn't be there. It couldn't have rolled there. A glacier dropped it there. Glacier that probably came out of this valley and melted it and dropped it right there. Melted there and dropped that there. When I lived in Ohio, there was a state park that I used to go to all the time with my friends. And next to the state park of this, next to the parking lot of the state park was a gigantic 2-story house-sized boulder of granite. Now, Ohio doesn't have any granite. Ohio is mostly Silurian, Devonian, and Ordovician limestones, shales, and sandstones. The glaciers have scraped pretty much everything else away. So why was there this massive chunk of granite there? Why is this object totally foreign to the area sitting there? Because during the last ice age, that mile-thick glacier was sitting on top of that location. It scraped away all the young rock, but you know what it left behind when it melted? That gigantic chunk of granite that it brought from Canada. Okay, that's a glacial erratic. I already mentioned when chunks fall off of glaciers into the ocean, we call that calving, right? That's how you get icebergs that float out into the ocean. The world's largest iceberg, how big is that thing? I want to say it's like the size of New Jersey. It's just like hanging out there in the Antarctic Ocean. I want to say. It's been a while since I looked it up, but it's huge. Okay. Or maybe the article I read was that it was about to fall off and become the world's largest iceberg. I don't remember exactly. But if that were to happen, whenever chunks of ice fall off into the ocean, they generally make tsunamis. All right, so let's talk a little bit about the landforms associated with glaciers. And to assist, I have a model. All right, so first things first, the valleys. And here's the camera. Okay, so we have our glacial valleys. I'll just swivel back and forth so you can see what I'm talking about. Okay, so we have our main glacial valley here and our sort of side valleys here that feed into that main valley. Glacial valleys generally are U-shaped in cross-section because they've been scraped and scraped and scraped into that shape by the continual passage of all that ice grinding away at the rocks on the side of the valley. They usually start off as stream valleys. Before this mountain was above the snow line, before it got shoved up that high, there was a stream, a nice, quiet little meandering stream making its way down the side of that mountain. And then as it got shoved higher and higher up until eventually it was high enough for snow to form, and then for the ice to form, and then the glaciers to form, it followed the path of least resistance downhill, which was going to be that already existing stream valley. So our tiny little V-shaped stream valley eventually got weathered and eroded out into this massive U-shaped glacial valley. Okay. Now, each little side valley here that feeds ice into this main glacier, we call that a cirque. C-I-R-Q-U-E. Cirque. Okay. Is that up there? It is. Good. I'm on the right slide. And then these ridges, these razor sharp ridges between all of these cirques and valleys, those are arêtes. A-R-E-T-E. Arêtes. And then where you have multiple arêtes that come together, like this one and that one and this one, and this one and that one and this one, you get these peaks. Those are called horns. So we have our glacial valley, cirques, arêtes, and horns. Okay. Now, let me ask you a question. What happens if I have an ice age? I'm going to hug my glacier here. What happens if I have an ice age, right? I got lots and lots of glaciers, lots of glacial valleys form, lots of glaciers making their way down. Where are all bodies of water trying to flow to?
The sea.
Yeah, sea level. Glaciers are no different. They keep trying to grind their way down to sea level. So eventually, any of them that are near the coast do make it there. So I have a glacier that makes its way to sea level. Then global climate changes, temperatures rise, my glacier melts. As my glacier melts, what happens to sea level? It rises. Okay, so I go from having a glacier that has found its way to sea level, okay, to all of a sudden having no glacier and sea level is significantly higher. Sea level now, let's say, is right here, right? Because all that ice melted. This is now a drowned glacial valley. We call that a fjord. You ever heard that word, fjord? There's lots of fjords in Norway. There's lots of fjords in Iceland. There's lots of fjords in Greenland. There's lots of fjords in Alaska. Wherever you have lots of glacial activity near the coast, you also have lots of fjords. And they are glacial valleys that are now flooded by the ocean. Fun historical fact, the fjords in Norway and those other northern European coastal countries were often used by Nazi submarines during World War II as bases. They would hide bases in there for those submarines to refuel and rearm. And American submarines had no idea. Like, it was a maze in there. They had no idea how to find anything in there. So they would, whenever they needed to get away in a hurry, Nazi submarines would just go into the fjords, and then that would be it. American submarines would lose them like that. And there's a theory that there are still several Nazi submarine bases that have not been found out there, which would be cool. Documentation, I believe, I've heard, has been found for several that were never found. So it's pretty cool. If anyone's feeling like Indiana Jones, you'll find it. Bless you. Okay. Oh, I forgot to go to the next slide. All right. Pardon my French. Roche Montagne, I believe is how this is pronounced. I looked it up once a couple years ago. I'm pretty sure that's how it was. A roche montagne is what happens when you have a hill that has the unfortunate destiny of being in the way of a glacier. Okay? Your glacier runs into your hill and then immediately starts crunching it down, right? Removing material, pounding it until eventually you end up with this ramp. Okay? So where once there was a hill, it kind of got pummeled down into this ramp shape. And you can always tell what direction the glacier came from because your ramp is going to be pointed in the direction that the force came from that removed all that material, right? So if I'm looking at this, I know that the glacier came in that direction, from that way towards that way. So my glacier kind of gets shoved up over the ramp and then kind of chunks and breaks off on the other side, continuing on its movement. You will often, when you're reading literature on the subject, I know you all read papers about glaciers all the time. But when you're reading those papers, you probably see that the sediment that is formed as a result of this glacial activity is called drift. Glacial drift is what people will often refer to this. I don't really like that term. It implies that sediment just kind of wandered its way there, I think. Till is another word for this, and you've actually seen me use that word already in our class in our sedimentary rocks lab. One of those rocks is tillite, perhaps you'll recall. That is the result of the sedimentary process doing its thing on glacial sediments. Okay, so we have till, which has been left behind by a melting glacier, which gets compacted and cemented into tillite. When I see tillite, I know there was a glacier there, right? Then we've got stratified drift or stratified till, right? which is what happens when you get really, really, really seasonal deposits of this material. And you can tell how long each season was, an extended melting season, an extended freezing season, by how thick and thin those layers of till are. You can do the same thing with little layers of microscopic dust. We call it rock flour, and they make tiny little layers we call varves. So if you have a very thick layer, you know there was a lot of melting that season, right? If it didn't melt, then there wouldn't be the dust there to be deposited, right? But if it's very thin, you know that the melting season did not last very long at all. And so we can get these interpretations about seasonal changes by studying these deposits of glacial sediment. Moraines are the structures that are built as sediment is picked up by our glaciers. There are several different types of moraines. The first kind is called a lateral moraine. Okay, a lateral moraine goes along the side of our valley, the side of our glacier. So here, right here, this dark stripe along the side here, that is a lateral moraine. There's one here along the side of this valley. There's one here along the side of this valley, and this one, okay? Lateral moraines go along the sides. This is what happens when our glacier is pulverizing and picking up all that rock from the side of our valley, okay? So lateral moraines along all the sides of our valleys. But as you can see, multiple glaciers come and join together. And when our glaciers join together, what happens to this lateral moraine and that lateral moraine? These two lateral moraines combine together and make what's called a medial moraine. You can see that in this picture as well. Look, this lateral moraine and this lateral moraine combine to make this medial moraine. This lateral moraine and this lateral moraine combine to make this medial moraine. So lateral, lateral, medial. Continuing down. It's that conveyor belt of sediment I talked about before. All of it eventually is making its way towards the front of the glacier, where eventually it's going to melt. And when that glacial ice melts, what does it leave behind? All the sediment from the lateral and medial moraines, right? Now, when that happens, we often get a buildup of sediment at the front of our glacier. We call that a terminal moraine. You can see that right here. Here is the front of my glacier. This pile of sediment in front of it is the terminal moraine. Terminal moraine right there. And if I show you the example without the ice on it, you can see the terminal moraine right here after all that ice is gone. Right? Those are the three types of moraines. All of them moving sediment downhill. Any questions? No? Okay, well then, ice ages often produce way more glaciers, right? As a matter of fact, let me give you the definition of an ice age. An ice age technically is a period of time when there is ice at both of Earth's poles. Which means, technically, we are still in the ice age. We never left, at least not yet. We might be making our way there right now. But this period of warming that we are in has not yet ended the ice age. When I say, and when I have said in the past, that the last ice age ended 11,700 years ago, what I'm actually talking about is the last glacial maximum. That's the last time glaciers advanced as far south from the northern hemisphere and north from the southern hemisphere as they have in a long time. Since that point, they have only been retreating, which means that we are in a period of global warming, but still in an ice age because there is still ice at both poles. If this warming trend continues to the point where there is no ice at the poles, first of all, I hope you don't have any beachfront property. Second of all, we will no longer be in an ice age. But technically, we are still in one. So, during the last glacial maximum, this is what the United States looked like. Compare this to where it was in that last photo I showed you of what it would look like if all that ice melted, right? The East Coast, huge. Florida, massive. Matter of fact, Florida and Cuba are practically the same, right? And there were probably a few land bridges there at one point or another, right? Gulf of Mexico, Gulf of America, way smaller, right? It's going to take so long to get over that. No San Francisco Bay, no Puget Sound, right? None of that. And look at the ice. Look how far south the ice is, right? That's that mile-thick glacier I was talking about before. Matter of fact, our Great Lakes exist because that glacier was there. Our Great Lakes exist because there's a combination of a bunch of material being removed by the glaciers, but also, how much do you think a mile of ice weighs? Yeah, I can't even begin to tell you how heavy that ice was. But you know what it did? You ever taken a memory foam pillow and put something heavy on it? You put some heavy on it, it pushes down the memory foam. What happens if you then remove that heavy thing quickly? Huh? Say that louder. I'm sorry. Yeah, there's an imprint until the memory foam slowly rebounds back upward, right? The same thing happens for continental crust. You're really cold, huh? When there was a mile of ice on top of our continental crust, it was so heavy that it pushed our continental crust down into the mantle a little bit. That took a long time to happen, but it only took about 12,000 years for all of that to fully melt away. That's the blink of an eye. That's less than the blink of an eye, geologically speaking. So it took a long time for this to happen, but then all of a sudden that weight was gone, all of a sudden, right? And it's still rebounding upward. Our Great Lakes exist there because of the imprint left behind by those glaciers. As our continental crust is slowly increasing, right? It's slowly rebounding upward. We call this isostatic adjustment, by the way. This will come up again later, okay? Isostatic uplift, isostatic adjustment, right? As it slowly rebounds upward, our Great Lakes are getting shallower. But all that water has to go somewhere, so where's it going?
The ocean. Into rivers. No.
What happens if I have a cup of water here, which I do, and then I somehow am able to push the bottom of this cup upward? The level of my water will rise, right? Until eventually it overfills, and then it has to go out. As my Great Lakes shallow, but keep the same amount of water, the water has nowhere to go but out. So our Great Lakes are getting shallower, but spreading outward, which is why cities like Chicago are already experiencing flooding issues. And it's only going to get worse as time goes on. What about Chicago?
I just said Chicago.
No, Chicago, yeah. That's all right. Chicago got get flooded, right? Sorry, I shouldn't say that. Sorry to anyone from Chicago. All right, for other reasons too, but okay. So this is what happens during a glacial period, okay? Coastlines, much larger. Why? Because sea levels are lower. More is exposed. As a matter of fact, if you look at that map right there, camera, you going to follow me if I look at that map? I don't know if it can turn around. We'll see. All right, follow me to this map. We're going on a field trip. Camera, are you going to stick with me? Oh, I think that's as far as the camera can go. But you see this white outline here around Florida in particular? Do you know what that is? That represents the zone of continental crust that is currently flooded by our ocean. Since that last glacial maximum, all of that has been covered in water. About 18,000 years ago, that started. About 11,700 years ago, it really started going, okay? I can actually go out there in a boat, and people have. You can drill down through the last 12,000 years of sediment and pull up fossils of animals. that lived on land. Why? Because that was all exposed during the height of the last ice age. Okay, there's fossils of plants and land animals and all of that out there that are currently covered in water.
The camera did not follow you back.
Boo. Come on, right here. I'm right here. Hi. Over here. You gonna behave? Yes, there we go. Thank you. Yes, I'm here. Keep following me. Good. All right. Now, what causes ice ages? Do they just randomly happen? You would assume not. I'm asking the question, and she's saying, obviously, that means it's not, right? What ideas do you have? What could cause an ice age?
Earth's tilt.
Oh, Earth's tilt. We're going right to it. Okay, sure. What else?
Like wobble.
A wobble. Okay, we'll come back to all that. Any other ideas? Claudia, any ideas for what could start an ice age? No? Trent, you got anything for me?
I do not.
Ice age?
Blanket cycle.
Have you looked at my slides already? No, you just know all this?
And blanket cycle.
Okay. Well, we'll get to that. There's a couple of factors that influence an ice age, okay? First of all, ice ages have been happening for at least the last 2 billion years. I say at least because rock older than 2 billion years is hard to come by, and any rock that's in a condition worthwhile to get any climate data off of is even harder to come by. So the last time that we can confirm, or the first time that we can confirm an ice age happened, is about 2 billion years ago. So this has been happening for a long time. However, the factors for what could cause it seem to have been changing. Now, early on in Earth's history, before I get there, let me remind you of something that keeps coming up. In general, all things in nature are seeking a state of stability. Good. As Earth is forming, and its atmosphere is forming, and its oceans are forming, all of these things are new, it's going to seek that state of stability. And so as volcanic activity goes up and down, and ash fills the atmosphere, and there's all these gases, greenhouse gases in the atmosphere, and then there's none, and then there's more, there's going to be ice age, no ice age, ice age, no ice age, until finally it finds parity, it finds that equilibrium. But then something else enters the field. Life. What does life do? What does photosynthetic life do? Let me ask you that. Sucks what in?
Carbon.
Carbon dioxide and other greenhouse gases, and puts what out? Oxygen. So greenhouse gases, which, remember, keep heat in to our atmosphere, make Earth warm, all of a sudden are being absorbed by these things that are doing this new thing. The new kid on the block is photosynthesizing organisms. And because there are so many greenhouse gases, right, they spread like crazy all over the planet, get lots of greenhouse gas, yummy eating, photosynthesizing plants, right, and algae and bacteria, and they do that, and they spit out oxygen, and all of a sudden we go from a warm carbon dioxide-rich atmosphere planet to an oxygen-rich atmosphere, which is not a greenhouse gas, does not keep heat very well, and our planet all of a sudden gets a lot colder. And then it happens again, and then again, and then again, and again, over and over and over. Life gets out of balance. It's interesting to think about, isn't it? Right now, the biggest thing on our minds is we're under threat because things are going extinct. Life is under threat from the conditions of our planet. But for so much of Earth's history, life has been the cause of its own extinction. Every time life gets out of control, there's too much of it, ice age. Kill things off. Stuff dies. until the next time the Earth finds an equilibrium. And then a new form of life shows up on the block. New forms of photosynthesis, C4 plants, trees, angiosperms, grasses. Every time something new shows up, it throws off the equilibrium. And oftentimes, an increase in photosynthesizing life results in an ice age that kills off a lot of that photosynthesizing life. How this works with evolution and the refining of gene pools and stuff like that, this is something that we talk about in 1404. Okay? We talk about this a lot more than this phenomenon. But that was a major cause of ice ages for a long time. It's been a while since we believe either life or a significant change in atmospheric chemistry has caused, or at least been the root cause, for an ice age. These days, it comes down to something else. What do you call it? Milankovitch cycles. What are Milankovitch cycles? Well, there are 3 ways that the Earth moves around its orbit of the sun. Earth's orbit of the sun, is it perfectly circular? No. Do you guys know that? We're not going in a perfect circle around the sun. We actually vary between a near circular orbit and what we call an elliptical orbit, like this, where at one point we're going in a near circle, right? And then at a different point, we're going in an elliptical, sort of egg-shaped orbit. This is on a cycle of about 100,000 years, where we go back and forth between those two. Then we've got obliquity, which is, you know why all of our globes are shown tilted like that? Why doesn't it show everything like this? Huh?
Because our axis is tilted.
Our axis is tilted versus what? We're in space. There's no point of reference.
The sun.
What about the sun?
We're tilted in reference to the sun.
But the sun is also just hanging in space. There's no reference for that either. Ah, yes, there is one point of reference for us, the plane of our orbit around the sun. So as we go around the sun, that plane, we are tilted versus that plane. Because we are tilted versus that plane, we have a certain line around our planet, okay, around which we get the most direct sunlight. Do you know what we call that line?
Equator.
The equator. And it is not straight across our planet. It is at that tilt across our planet because we are tilted versus that plane. Okay, so our obliquity is our motion around the sun along that plane. Okay? And then we also have something called the precession, which is that wobble you were talking about. Earth isn't only at this plane spinning and moving around the sun, it's also doing this. We believe this wobble occurred because of an impact the Earth experienced early on in its life that created the moon. A second planet slammed into Earth. Have you heard about this? This is how our moon was formed, we believe. The moon is a chunk of debris blasted off our planet when another planet hit Earth. That other planet, we call it Theia, which is a name I campaigned really hard for my daughter to have, but did not work out. But Theia and early Earth slammed into each other. A chunk of debris got blasted off, and that became our moon. But we believe that this precession exists because of that impact. So we have precession. We have axial tilt and spin. And then we have eccentricity. So Earth in space is really doing this around the sun. Are you getting sick? Moving at hundreds of thousands of kilometers an hour through space. These things all eventually add up to certain factors. Namely, that when the Earth is the furthest from the sun, we are already receiving less solar radiation, right? But also, if precession and obliquity add up so that the side of the planet with the most water and ice, for example, this side, is facing the sun at the same time that we are already really far from the sun, we are not going to absorb energy as easily on this side. As a matter of fact, we're going to reflect it in some cases, right? If it hits ice, it will reflect. If it hits the ocean, some of it reflects. but it gets absorbed a lot slower, right? So when that happens, Earth for that period of time is going to receive less energy. If it receives less energy, there's less heat. If it receives less heat, what happens to our snow line? It gets lower. As our snow line gets lower, more snow can remain year-round, making that glacial ice. As more glacial ice is made, that's more ice that can reflect solar energy. As more solar energy is reflected, Earth receives less energy, receives less heat. As less heat is absorbed, the snow line gets lower. As the snow line gets lower, more snow can remain year-round and more ice is made. As more ice, you get the process. This is what's called a positive feedback loop. Okay? It is self-sustaining. It pushes itself forward. And the result is an ice age. Okay? Until something changes that new equilibrium. Perhaps, say, an excess of carbon dioxide in the atmosphere, once again retaining more energy, melting that ice, which is what's happening to us right now. This is a natural cycle, people, caused by factors outside of human control. What I'm trying to emphasize to you here is, yet again, and I've said it before, and I'll say it again today, and I'll say it again in the future, no doubt, climate change is natural. It happens on its own. What's different this time is that we have aggravated it. You'll see a term thrown out there called anthropogenic climate change. Do you know what that means?
Man-made.
Man-made. Man started. Man created climate change. I am strongly opposed to that term. We did not start it. This started thousands of years ago, long before humans were doing anything other than learning how to smelt iron, right? What it is anthropo-aggravated climate change, which isn't a real word. I need to come up with a smoother one. I haven't thought of one yet. Anthropo-worse? That's not better. Huh? Anthropo-worsen? Yeah. We've made it worse. We've aggravated it. It's going to be worse than it would have naturally because of our contributions, but gosh darn it, we didn't start it. It started a long time ago because of factors outside of our control. You understand why? Do you understand a little bit more about that now? I hope so. Okay. Any question about Milankovitch cycles or about climate change or any of that? This is the great opportunity, since we're already on the subject, to talk about your questions about climate change.
We're in a cooling cycle right now, right?
A cooling cycle?
Yeah.
No, we're still in a warming cycle.
No, I mean like relative to the Milankovitch cycle. Like
Where we are in the rotation. Yeah, we're in a different positive feedback loop. Because think about what happens on the other side of that loop, right? I talked about the ice age inducing feedback loop. But what about the opposite? What if my snow line keeps increasing? I get less ice, therefore less glaciers, therefore less reflected energy, and therefore more energy retained. And then it keeps advancing upward. So even though, yes, we are technically in what should be, mathematically speaking, I say should be, right? A cooling cycle as far as Milankovitch cycles are concerned, we are already in the midst of a positive feedback loop towards global warming. Okay? So it may be tempered a little bit by a few of the factors, but this is still the path that we're on. These kind of global scale changes don't happen every 100,000 years. We get minor ones on tens of thousands of year scales and major ones on 200 to 300,000 year scales. We don't know yet if what we're looking at right now is a major one or a minor one. In 1,000 years, we could be looking at no ice whatsoever on any of our poles. Or we may have, by then, gone back into a cooling phase. What else? What other questions? Nothing? Okay, well, you don't have to ask them today. You know you can ask me questions anytime. All right. Well, if there are no more questions or comments, that's it for the lecture today. I have no new lab for you. I will be giving you lab 5 next week, but it has nothing to do with samples or identification. It's all about reading maps. Okay, that'll be fun. It'll be different. It'll be a group assignment. You'll need to find a group and work on it together, ideally. For those of you working on it online, you don't need to get a group, obviously, but you can form one. If any of you ever want a group at any point during the semester, all you have to do is discuss in GoReact who you want to be in that group. And then one of you, please pick who it will be, can send me an email saying, hey, this person, and this person want to be in this group. And I'll make you a private discussion board so you guys can discuss your group activities together in private. The rest of you, you can discuss that amongst yourselves here. Okay? All right, well, I'm going to go ahead and end the recording here.